Fusion energy has been in the news a bit, and people have been asking us, right now, where does LPPFusion stand relative to other companies in the fusion energy race? So in this new video series, we're going to try and separate hype from reality. And I think we're going to find that reality is a lot more encouraging than the hype. We're going to do two things. First, we're going to discuss the basic different paths that people are taking to fusion energy. And then we're going to discuss individual companies and their claims and how we stand relative to those companies. So let's get started. There are basically two things that separate the different paths to fusion energy. One is different fusion fuels, and the other is the different approaches to confining the hot plasma where fusion takes place. And just to remind you, plasma is very hot gases where the electrons are separated from the atoms and are free to move. So let's start with the fuels. There are basically two different approaches to the fuels. One are fuels that are derived from the heavy isotopes of hydrogen. An isotope means that for a given nucleus of a given element, which means a certain number of protons, there are a different number of neutrons. So in the isotopes of hydrogen, ordinary hydrogen has a single proton and no neutrons. Deuterium, which is the source of the fuels for the first approach, has one proton and one neutron and is pretty abundant in seawater. So the fuels for this first approach to fusion energy are derived from deuterium because they're not found in nature. The other approach, which is the approach that LPPFusion and some other companies use, is based on a combination of ordinary hydrogen, which is found in water everywhere, and boron-11. Boron-11 is the dominant, most common isotope of boron, and it's abundant in nature. Let's first look at the deuterium fuels. The main deuterium fuel is deuterium plus tritium. Now, tritium, the third isotope of hydrogen, is not found in nature because it's radioactive and it decays in only 14 years. So, as this diagram shows, you have to breed the tritium from the tritium-deuterium reaction. So you use a certain starting amount of tritium that you get from ordinary nuclear fission, nuclear energy reactors, and you use it as a seed to start the cycle going. As you can see, the reaction of deuterium and tritium produces a neutron. You smash that neutron into beryllium. Beryllium produces 2 helium and 2 neutrons. So it's multiplying the neutrons so that when the neutrons interact a third time with lithium, you get 2 tritium. So you're breeding or multiplying the tritium that you start with, and you get more and more fuel, and you can build up your fusion reaction. After the start of this cycle, it can continue without any new inputs of tritium from fission generators. If it works, it will be self-sustaining. This is the first disadvantage of this approach. As you can see, it's pretty complicated to actually get your fuels because you can't find them in nature. If you look at this diagram of the tritium production building in ITER, the ITER reactor that's under construction in France, you can see it's a pretty sizable operation to get this tritium, which is a gas, out of the lithium, which if you heat it becomes a liquid. And it's pretty expensive. tritium is not the only fuel you can derive from deuterium. You can also derive helium-3 from deuterium. But only one company, Helion, is working on that approach. So we're going to discuss that when we get to the individual companies. But right now, let's just focus on deuterium and tritium. There's a second big disadvantage to this approach, which is the energy comes off mainly in the form of a high-energy neutron. Now, because a neutron is neutral, the only way to get energy out of it is the way we've been producing electricity since the time of Edison, which is to use a source of energy, in this case, the neutron, to heat water, to produce steam, to drive a steam turbine, to drive a generator, to produce the electricity. Now, turbines and generators are big, complicated, and expensive machines. Roughly speaking, it takes $1 million to produce a turbine that will produce a megawatt of power. Another way of looking at it is 7 tons of machine for a megawatt of power. Since at this rate, we're investing as much money just in the energy conversion as is needed for some forms of conventional energy, we're not going to be able to reduce the investment cost of fusion energy with these fuels below the costs of present-day electricity. Now, that doesn't mean we can't reduce the overall price, because the overall price of electricity today from fossil fuels includes the very significant cost of the fuel itself. With fusion, the fuel really doesn't cost hardly anything. Because with fusion, even with tritium, the fuel is much cheaper than fossil fuels. So you could produce cheaper electricity, but you'd still need a fairly large amount of investment. Second big disadvantage is that the neutron you're getting the energy from is very destructive. This is a 14 MeV neutron, million electron volt neutron. So it smashes into the structure that the device is made of, and it transmutes the nuclei in that structure into other elements. Many of them are radioactive elements, so you have the problem that you're dealing with a radioactive structure over time. But even more significant, you're weakening and destroying that structure. So what you have to do is you have to spread out the neutrons so they're not so destructive. And that means building very large devices. Large devices means expensive devices. We'll get into this more in the next stage where we discuss various types of devices. But there are limits to how small you can build a deuterium-tritium fusion generator for a given amount of power. And that's another a disadvantage, because, of course, we want cheap power. So with these disadvantages, why has most of the money in fusion energy gone into DT fusion? Well, the basic reason that people were initially attracted to it is that fusion energy only occurs at high temperatures. And DT fusion is the fuel that has the lowest burning temperature. So DT fuel burns at about 40 keV, 40,000 electron volts. That's the equivalent of 440 million degrees Kelvin. Which doesn't sound very cool, and it isn't. It's about 40 times the temperature at the center of the sun. But it is considerably cooler than the temperature that other fuels burn at. So that's why people started to focus on this approach. Now, a word from our sponsor. Tired of inflation, wars, and inequality caused by the energy crisis? LPPFusion is developing a solution that could allow everyone to have cheap, clean, off-grid, and sustainable fusion energy. Invest now as we seek to bring this potentially life-changing technology to market. For more information, visit wefunder.com/LPPFusion. So what's the other approach? The other approach is hydrogen plus boron, the approach LPPFusion and other companies are using. The advantages of this approach are sort of the converse of the DT approach. First of all, these fuels are abundant in nature. You don't have to breed them. You just find, obviously, hydrogen is present in water everywhere. Boron is pretty abundant in nature. The amount of boron that we mine today is 10 times the amount of boron we would need to supply all the energy needs of the world at present. And if at some future point we run out of boron on the land, in the oceans, boron is a major constituent of sea salt, so we have enough boron for billions of years of energy at the present rate of use. It's abundant and it's directly available. Second big advantage, and this is the biggest advantage, is when boron and hydrogen interact, as we see here, they produce 3 helium nuclei and no neutrons in the primary reaction. So the energy comes off as the motion of these helium nuclei, which are charged. So the motion of charged particles, that's the definition of electricity. So we are producing electric currents in the plasma, which can be converted directly to electric currents in a circuit by various means. And that is much cheaper than the way we've been doing it since Edison with the steam turbines and the steam generators. So if you look, for example, at this way that we're doing it at LPPFusion, which we'll go into in later episodes, it's a much smaller and much more compact device for the same amount of energy. It's about 0.2 tons per megawatt instead of 7 tons per megawatt. So that means it's about 30 times less mass per unit power output. And we've done rough estimates that this can be produced for about 10 times less capital than the turbines and generators. Now, people say, 10 times, how do you know it's exactly 10? No, we're saying it's roughly 10 times. We won't know until we actually produce these. But you can see that it's 30 times less massive. We think 10 times less cost is a pretty good estimate. So that eliminates that floor, and we can produce this part of the device for much less money than existing power sources. Second of all, we don't have the problem of the destruction of the device by the neutrons. So the device itself can potentially be much smaller and get out much more energy per unit mass. Again, we'll discuss this more when we discuss the different approaches to confinement. In addition, we're not producing any radioactive materials that have a significant half-life. During the operation of a hydrogen-boron machine, some very short half-life materials, such as carbon-11, will be produced by secondary reactions that don't occur very often. But carbon-11 has a half-life of 20 minutes, so very soon after you turn off the machine, it would have decayed down to nothing. So we have a machine that doesn't produce any radioactive waste, can be located close to the load, decentralized, and basically has no safety issues. When you turn it off, and there's basically no energy left. So the disadvantage of this approach is that boron and hydrogen must be heated to hundreds of keV, not tens of keV, billions of degrees Kelvin for them to burn. People thought this was a really big disadvantage, but our company and other companies have already achieved these very high energies that are needed to burn this material. We haven't gotten all the conditions together that would make this net energy producing. We're not there yet, but the temperature barrier has already been exceeded by several different methods working with hydrogen-boron. So it wasn't as much as a problem, and that's why more and more companies are getting interested in the hydrogen-boron approach, because it can produce very cheap energy and potentially is a much shorter route to fusion energy. So that gives you an idea of the first division in the paths to fusion energy. In the next episode, we'll get into the second division, which is how do you confine the plasma? It's either with external magnetic fields produced by magnets that you build, or by internal magnetic fields that are produced by currents flowing through the plasma. We'll get to that in the next episode.